lesson 10.2.1. I really do enjoy this chapter. I think it's pretty neat. So there's a lot of cool properties of circles. So how far across is it? Introduction to chords. You already know how to determine the diameter of a circle if the entire circle is in front of you and the center is marked, or if you know the radius of the circle. However, what if you only have part of the circle, an arc? Or what if the circle is so large that it is not practical to measure its diameter using standard measurement tools, such as measuring the diameter of the equator? So today you will consider a situation that demonstrates the need to learn more about the parts of a circle and the relationships among them. 1048, the world's largest tree. I have no idea how to say this. Baobab? No idea. Tree is a species of tree found in Africa and Australia. It is often referred to as the world's widest tree because it has been known to be up to 45 feet in diameter. While digging an archaeological site, Rafi finds a fragment of fossilized baobab tree that appears to be wider than any tree on record. However, since he does not have the remains of the entire tree, he cannot simply measure across the tree to determine its diameter. He needs your help to determine the diameter of this ancient tree. Assume the shape of the tree's cross-section is a circle. So this is going to be representative of the arc of the tree that he found. So we're going to go to this resource page, and on it we're going to locate AB, arc AB, that represents the curvature of the tree fragment. We're going to trace this arc on a tracing paper. Obviously I'm not going to do that. Then decide with your team how to fold the tracing paper to locate the center of the tree. Hint, this will take more than one fold. Be ready to share how you found the center with the class. So what we're going to do is, if we go here, sorry. That didn't go well. Let me close this out, I guess, and try reopening it. Okay, so we get something like this. And the long story short is, if we had just taken some points on this and folded it, again, you're going to have to imagine that it's tracing paper. But if I had just put 2 points on the arc and folded it over, so where this was the middle, and I'll do the best I can with this. Again, hopefully you'll get enough to sort of imagine what's happening, if not exactly what's happening. But if I fold it, I would get something that looked like that, right? It would be just a fold right down the middle. And same thing, if I did the same thing and let's say I folded it in half this way, I would get something that was roughly, roughly there. And what if I folded it in half from here to here? I would get something that's roughly like this, half and half. So what you can see is, no matter where, as long as I pick 2 points on the arc and fold it, I get to sort of cut that circle in half. And if I do enough of those, I end up with the center of the circle, which I think is pretty cool. Now what we can do is we can go back and we can say, all right, well, we should be able to sort of measure this, because this would be the center of the circle. So this radius should be the same no matter what, from the center to the outside. So that's how we would do it. Again, just multiple folds, picking 2 points on the arc and folding it down the middle. Picking 2 other points, folding it down the middle. 2 points should be enough, but we could do as many of them as we wanted. Then it said if 1 centimeter equals 10 feet, well, I guess let's run back over and keep going with this. But again, I think that's a pretty cool property, and I hope that we're picking this up because I know I don't have graph paper in front of me. But essentially, if you just take 2 points on an arc and fold it in half, you'll get something in the middle. Then if you take 2 different points on the arc and fold it in half, you'll get that was a really bad one. You'll get, boy. You would think. Yeah, you get the idea. Okay, so that one is a better one. So you'll get that middle. If we cut this in half, we'll get something. And again, they would all meet at the center. So just folding it in half. I would love to have had those 45 seconds back. I feel like I made the video way worse than better, that's for sure. All right, so as we go along, it says in part A, you located the center of the circle. Use a ruler to measure the radius if that circle is 1 centimeter, represents 10 feet. Well, we go ahead, we measure it. It turns out it's 2.5 centimeters. So we multiply that by 10, and it ends up being 25 feet of a radius. Well, if the radius is 25 feet, that means the diameter must be 50. So that would be bigger. He found part of the world's biggest tree, or whatever, because 45 up to this point. 45 diameter was the biggest, but we had a 25 radius, which doubles to a 50 diameter. So there you go. He found the biggest tree. Good for Rafi or Rami or whatever his name was. All right, so 1049, parts of a circle, part 1. A line segment that connects the endpoints of an arc is called a chord. So again, that was what we did. We connected 2 points on an arc. This was called the chord. It's important that we know what that is. And that chord sort of folded in half and made this. Now, if we think about what happened here, we know that this distance has to be the same. Obviously, this distance has to be the same. And clearly, this distance has to be the same because we folded it in half. So these halves have to be equal. This is obviously equal because it is reflexive. And this distance has to be the same because it was folded in half. These were on top of each other, right? They reflect across. So we have side, side, side congruence, which tells me that I have a perpendicular bisector right there. So I have a 90-degree angle, which is kind of cool. So again, kind of neat. Grab a piece of paper, draw a circle on it, use a compass if you have one to make it a good circle, and start folding it in half. And I think you'll see some pretty interesting properties emerge in terms of right angles and in terms of finding the center of that circle. Again, that's sort of where we're at right now with that discussion. So one way to locate the center of a circle when given an arc is to fold it so that 2 parts of the arc coincide or lie on top of each other. If you fold AB so that A lies on top of B, what is the relationship between the resulting crease and the chord AB? Well, like we said, we know it's cut in half. And then it says, and again, we know that's true because they reflect across this line, right? I mean, obviously, if they were on top of each other, that says that they have the same distance. So the tree fragment in problem 1048 is an arc between points A and B. However, the missing part of the tree formed another larger arc of the tree. So with your team, locate the larger arc with endpoints A, B, and trace over it in different colors. So here's what they're saying. They're saying this, that if we look right here, and I'll make this red. If I call this arc AB, you'll notice I'll make that arc sign. It's not a line. I made an arc. Well, what if I change the color? And now I want to talk about this part of the arc because it also goes from A to B, right? Well, you can see this is bigger than this one. So maybe what we should call this is A, and just pick another point. It doesn't have to be X. In this example, we use XB. So now if I say AB, you know I'm talking about the short way or the minor arc. However, if I say AXB, you know I'm talking about the longer way around or the major arc. So make sure you understand the difference between a minor arc and the fact that you only need 2 letters to name it, and a major arc and the fact that you need 3 letters. And again, you're allowed to put your own point in. So if you didn't have that point, you could add a point in and go ahead and go with that. But the difference between a minor arc and a major arc. So at that point, we're going to skip problem 1050 and we will go to 1051. And that didn't work, so I'll close out of this and then reopen this. Like I said, skipping 1050, going down to 1051. So it says, what if you're given 2 non-parallel chords in a circle and nothing else? How can you use these chords to locate the center of a circle? Which is, again, pretty cool. So we can go back to this one, which we had already had open, which was at the recycling page. Now we're going to go down to the bottom of it. And here's what they're saying. This is part of a circle, and there's a circle out here somewhere, but this cuts that circle a chord, and this is a chord. So what would we do? Well, what we would want to do is we would cut it in half and get that perpendicular. And again, it'd be easier if this was a printed piece of paper. I could fold the paper in half from this point to this point, and I would get something along the lines of a perpendicular bisector. I'm not sure that's perfect, but it's okay. And again, then I would fold this in half and I would get another perpendicular bisector, and again, it would look something like that. Now this would become the center of my circle. And from the center of my circle, and I don't think I have any hope of this working out terribly well just by the nature of how this is supposed to go. But the long story short is, if we pretend that I could draw a circle that would hit all these points, you would be able to see that that's the center of it. That circle's not terrible. You kind of get a feel for what I'm trying to accomplish, I think. So if we go over here, cut this one in half, and again, we get something like, I don't know, maybe like that. And then same thing, if we cut this one in half, we get something maybe, it's pretty difficult for me to figure out exactly what the center is. I wish I could just start from the center and draw a circle out, but that's not how this works. So I'm left trying to guess where the circle would be and kind of go around it. So the second one's not as bad. So you can kind of see that would be the center of that circle. But again, just the idea that you can fold these in half, you get your you get your corners. You get your corners. You get those 90-degree angles and the center of your circle. So sorry this looks so terrible. I hope it is, again, okay with you understand what I'm trying to say here, as that came up poorly. But really, I think the best thing to do is draw a circle on a piece of paper and start folding it in half on the arcs. I think if there's any confusion about what you're saying, it'll definitely clarify it right up, I think, at that point. So 1051, describe how to locate the center of a circle without using tracing paper. Again, just fold the arcs in half and that'll find the middle. So 1052, it says examine chord WX, and the center is Z at the right. WX equals 8. So this distance here, from here to here, is 8. We have a radius of 5. So what does that mean? Well, I get this triangle. If you think about it, I get a triangle that looks something like this. And it's asking me, how far is this line from the center? Well, if I draw a right angle, you can see that this must be 4 and this must be 4, right? That 8 would get cut in half. We know it would get cut in half because we'd get that perpendicular bisector straight to the center of the circle. Well, the Pythagorean theorem says 3 squared plus 4 squared equals 5 squared. So the distance would have to be 3. Again, so just to kind of go through this one more time, if I were to take this and fold it in half, I would get the perpendicular bisector, right? I know that these halves are equal. That's a 4 and that's a 4 because it said the whole thing was 8. I know that this is 5 because it's the radius. Well, then 3 squared plus 4 squared equals 5 squared. So the distance would be 3.